Hello and welcome. Today we are diving into one of the most fascinating and fundamental concepts in computer science, the halting problem. It is a famous undecidable problem and holds immense significance in the field. So, what exactly is the halting problem? Here is the main question. Given a computer program and an input, can we determine whether the program will halt, meaning terminate, or run forever? In other words, can we create a universal algorithm that can analyze any program and predict whether it will eventually stop or continue running indefinitely? To understand the problem better, let us look at some simple examples. On the left, we have a program that halts. This simple program iterates through a loop 5 times, printing the numbers from 0 to 4, and then terminates. Determining that this program halts is straightforward. On the right, we have a program that runs in an infinite loop. This program continuously prints the message running and never stops. Identifying that this program will run forever is also quite simple. The real challenge arises when we ask, can we write a general algorithm that takes any program and its input and determines if it will halt? Is there a universal halting detector that can analyze all possible programs and accurately predict whether they will halt or run forever? This is the essence of the halting problem. Alan Turing, a pioneer in computer science, famously proved that such a universal halting detector cannot exist. He used a proof by contradiction to demonstrate this. Let us go through the proof. First, let us assume that there exists a halting detector, which we will call H, that takes a program P and an input I. H returns true if the program halts on input I, and false otherwise. Then we will show that this assumption leads to a contradiction. Next, we construct a paradoxical program that leads to a logical contradiction, proving that the halting detector, H, cannot exist. This paradoxical program is the key to understanding Turing's proof. Here is the code of the paradoxical program. This program takes another program as input. It uses the hypothetical halting detector, H, to check what happens if the input program runs with itself as input. If H says that program will halt, then paradox enters an infinite loop. Otherwise, paradox returns and halts. The crucial question is this: what happens when we run paradox with itself as the input? In other words, what happens when we run paradox? Let's consider the two possible cases. Case 1. If H says paradox halts, then paradox enters an infinite loop, which contradicts what H predicted. Case 2. If H says paradox loops, then paradox returns and halts, which again contradicts H's prediction. In both cases, H contradicts itself. Therefore, H cannot exist. It is impossible to create a universal halting detector that can correctly determine whether any given program will halt or run forever. The halting problem has significant theoretical and practical impacts on computer science. Theoretically, it proved the fundamental limits of computation and established the concept of undecidability, showing that some problems are inherently impossible to solve algorithmically. Practically, it influences compiler design, program analysis, and software verification tools, guiding the development of more robust and reliable software systems. In conclusion, the halting problem demonstrates that some questions about computer programs are fundamentally unanswerable by any algorithm, highlighting the inherent limitations of computation. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.